close your eyes now, and let me take you on a gentle journey to our closest companion in space. The moon has watched over Earth for more than 4 billion years, patient and constant, pulling our tides and lighting our nights. And now, in your mind, we're going to explore something remarkable. We're going to walk through the slow, careful process of making the moon our second home. You don't need to think too hard about any of this. Just let the images wash over you, soft and easy. Picture yourself floating toward that silver gray sphere, watching it grow larger in your window, seeing the ancient craters come into focus one by one. There's no rush here. Time moves differently when we talk about the moon. Everything happens slowly, deliberately, like dust settling in airless silence. Take a deep breath, and let's begin. The moon has been waiting for us. Not in any hurried way, but in the patient manner of celestial bodies that measure time in eons rather than heartbeats. For all of human history, we've looked up at that pale disk in the night sky, and the moon has looked back, unchanged, unchanging, holding its secrets in silence. When you first approach the lunar surface, the thing that strikes you is the stillness. There's no atmosphere to catch the light and scatter it into blues and golds. The sun simply shines, harsh and direct, painting half the moon in brilliant whites and grays while the other half disappears into absolute blackness. The shadows here are darker than any shadow you've ever seen on Earth because there's no air to soften them, no reflected light to fill them in. They're pure and complete, like looking into the depths of space itself. The surface stretches before you in gentle rolling waves of ancient dust. This dust, this regolith, has been forming for billions of years. Meteorites, some as small as grains of sand and others as large as mountains, have been pounding the moon's surface since the solar system was young. Each impact shattered rock into smaller and smaller pieces, grinding it down over incomprehensible stretches of time into a fine gray powder that covers everything. If you could run your fingers through this dust, it would feel strange. Not quite like beach sand, not quite like powder. The grains are sharp and jagged because there's no wind or water here to smooth them down. They've never tumbled in a stream or blown across a desert. They're angular fragments of stone, each one a tiny fossil of some ancient collision. And yet, despite their sharpness, they pack together into a surface that's surprisingly firm beneath your feet, compressed by their own weight and by the countless impacts that have tamped them down over geological ages. The craters spread out in every direction, overlapping circles within circles, the history of the solar system written in circular scars. Some are so large you couldn't see their edges from the center, like standing in a massive bowl 50 or 60 miles across. Others are small, fresh, their rims still sharp and defined, perhaps only a few million years old. In lunar time, that's practically yesterday. The oldest craters have been worn down by more impacts, their edges softened and rounded, partially filled with debris from newer collisions. Look closer at the larger craters, and you'll see they have central peaks, mountains that thrust up from their centers where the bedrock rebounded after the impact, like a slow-motion splash frozen in stone. Some of these peaks catch the sunlight at angles that make them glow against the darker crater floor, tiny beacons in the monochrome landscape. Between the craters, there are Maria, the dark plains that ancient astronomers thought were seas. They're not seas, of course. They're vast sheets of frozen lava, billions of years old, places where the moon's interior was once hot enough to melt and flow. The lava filled in the low areas, the giant impact basins, and then cooled into smooth plains of basalt. This rock is darker than the highland material, which is why the Maria appear as dark patches when you look at the full moon from Earth. These are the features that make the face, the eyes, and mouth of the man in the moon that humans have seen since they first looked up. The Maria are smoother than the highlands, with fewer craters, but they're not perfectly flat. Here and there, you'll see wrinkle ridges, long low folds in the lava where it compressed as it cooled. You'll see rills, channels where lava once flowed in rivers, now frozen in time. Some of these channels have collapsed roofs, creating chains of craters like beads on a string, marking where underground lava tubes once carried molten rock from one place to another. And everywhere, covering everything, is that fine gray dust. It's not quite gray, actually. In the right light, It has hints of brown, tinges of tan, subtle variations that depend on the exact composition of the rocks that were ground up to make it. But mostly, it's gray. A soft, neutral gray that absorbs most of the light that hits it, making the moon's surface one of the darkest in the solar system, despite how bright it looks from Earth. The temperature here swings wildly. In the direct sunlight, the surface can reach 260 degrees Fahrenheit, hot enough to boil water if there were any water to boil. But step into shadow, and the temperature plummets to nearly 300 degrees below zero. There's no atmosphere to hold the heat, no blanket of air to moderate these extremes. Heat radiates directly into space, and the shadowed areas become as cold as the void itself. But there are places, special places, where the temperature stays more constant. Near the poles, there are crater floors that never see sunlight, places where the sun's rays have never touched in billions of years. In these permanently shadowed regions, the temperature hovers at around 370 degrees below zero, cold enough to trap water ice, cold enough to preserve volatile compounds that would evaporate anywhere else on the moon. These are the cold traps, the freezers that have been collecting ice for geological ages. And in contrast, there are peaks near the poles that catch almost constant sunlight. The moon's axis is tilted only about 1.5 degrees from vertical, which means the sun never climbs high in the polar sky, but it also means that high points near the poles can stay in sunlight for months at a time, spinning slowly through the lunar day without ever dipping into shadow. These are the peaks of eternal light, and they're warmer, more stable, bathed in perpetual twilight that never quite becomes day or night. The moon is tidally locked to Earth, showing us the same face always, spinning on its axis at exactly the same rate it orbits our planet. A day on the moon lasts 29.5 Earth days, 14 days of sunlight followed by 14 days of darkness. During the long lunar day, the sun crawls across the sky, moving slowly enough that you could watch your shadow shrink and grow and stretch across the landscape over the course of weeks. There's something peaceful about a world without weather. No clouds ever cross the black sky. No rain ever falls. No wind ever blows. The footprints left by the Apollo astronauts more than 50 years ago are still there, perfectly preserved, and they'll remain for millions of years until enough micrometeorites hit the exact same spots to erase them grain by grain. This is the surface that's been waiting for us. Ancient beyond measure, preserved in a vacuum that's kept it almost unchanged since the solar system was forming. A world of light and shadow, of searing heat and absolute cold, of silence so complete that it feels like you could hear the stars themselves if you listen carefully enough. And now, slowly, carefully, we're beginning to make it home. The first structures we build on the moon will be small, humble, almost apologetic in the face of that vast emptiness. You have to start somewhere, and on the moon, you start simple. The earliest habitats will arrive folded up inside cargo landers, compressed and compacted, waiting to expand. Picture the first landing site, chosen carefully after years of orbital surveys and robotic missions. It's probably near one of those polar regions where the sunlight is more constant, where nearby craters hold water ice in their shadowed depths, where the terrain is flat enough to land safely but elevated enough to catch the sun. The lander touches down gently, its legs sinking slightly into the regolith, creating 4 new dimples and a surface that's been largely undisturbed for millions of years. Robots emerge first, or perhaps astronauts in bulky spacesuits moving with the strange bouncing gait that lunar gravity demands. They survey the immediate area, checking that everything is stable, that the ground is solid, that no large rocks or steep slopes threaten the construction site. And then, slowly, they begin to unpack. The first habitat might be an inflatable module, something like a heavy-duty balloon made of multiple layers of high-strength fabric. Folded up, it's compact enough to fit in the lander. Expanded, it becomes a cylinder 20 or 30 feet across, large enough to stand up in, to move around in, to live in. The robots, or the astronauts, carefully position the folded module on a flat area, connect it to power and life support systems, and then step back as pumps begin to fill it with air. The module expands slowly, taking shape over the course of hours. The fabric is tough, reinforced with Kevlar and other materials that can withstand micrometeorite impacts and the extreme temperature swings. Layer by layer, it inflates, the walls becoming rigid as the internal pressure builds. The outer layer is white or silver, reflective, designed to bounce away as much of the sun's heat as possible. Beneath that are insulating layers, then structural layers, and finally an inner layer that will become the walls of home. But an inflatable habitat alone isn't enough protection. The moon has no magnetic field, no atmosphere, nothing to shield its surface from the constant rain of radiation from space. Cosmic rays and solar particles stream in unimpeded, and over time, this radiation would be harmful to anyone living inside. So the habitat needs shielding, and the moon itself provides the material. The robots begin to pile regolith onto the habitat, carefully, methodically. They scoop up the gray dust and pour it into bags, or they push it into place with small bulldozers, creating a berm around the base of the habitat, then working upward. Layer by layer, they bury the inflatable module under several feet of lunar soil. The regolith is an excellent shield. It's essentially rock dust, dense and effective at absorbing radiation. A few feet of it provides as much protection as Earth's atmosphere does. As the habitat disappears under its blanket of gray, it transforms. What started as a technological object, something human-made and artificial, becomes part of the landscape. From a distance, it might look like a gentle hill, a low mound on the lunar surface, barely distinguishable from the natural terrain. Only a few elements remain visible: the airlock door, perhaps some communication antennas, solar panels arrayed nearby like mechanical flowers turned toward the sun. Inside, the habitat is being prepared for life. The walls are lined with equipment, lockers, storage bins. There's a sleeping area with restraints or sleeping bags to keep you from floating around in the low gravity. There's a work area with computers and communication equipment. There's a tiny bathroom, or at least the lunar equivalent, with systems to recycle every drop of water, every breath of air. Nothing can be wasted here. Everything must be used and reused endlessly. The lighting inside is soft, tunable to mimic the cycle of day and night that humans need to stay healthy. During the 14-day lunar night, when outside is absolutely dark, the lights inside maintain a rhythm that keeps your body's internal clock synchronized. During the 14-day lunar day, when the sun blazes down without pause, the habitat's lights can dim to create an artificial night, giving you the darkness you need to sleep. The air is carefully controlled, filtered, and cleaned continuously. Scrubbers remove carbon dioxide, oxygen generators split water into hydrogen and oxygen, replacing what you breathe. The temperature is maintained at a comfortable level, warm enough to be pleasant but not so warm that the cooling systems have to work too hard. Energy is precious here, even with solar panels, so every system is designed for efficiency. Living in these early habitats will be like living in a small apartment or perhaps a large closet. Space is limited. Privacy is minimal. Everything has its place, and clutter is impossible because there's simply nowhere to put anything extra. You learn to be organized, to be tidy, to appreciate the small comforts that make life bearable. But as more missions arrive, as more modules land and expand and get buried under protective regolith, the settlement grows. Habitats are connected by tunnels, also inflatable, also buried, creating a network of living spaces underground. You can move from one module to another without going outside, walking through passages lit by LED strips, your feet barely touching the floor in the light gravity. Some of the later structures are more permanent, built from lunar materials rather than brought from Earth. There are experiments with sintering regolith, using focused sunlight or microwaves to heat the dust until it fuses together into a solid ceramic material. Robots can print structures layer by layer, building walls and domes from the lunar soil itself. These structures are heavy, massive, impossible to move, but they provide excellent protection and they don't require shipping materials from Earth. Imagine a dome printed from regolith, a shallow arc rising maybe 20 feet high at its center, covering an area the size of a basketball court. Inside, the air is breathable, the temperature comfortable. The curved ceiling is the actual lunar surface, fused into a solid shell, with lights mounted to make it feel less oppressive. This is a common area, a place where the small lunar community can gather, share meals, talk, exercise, do all the things that humans need to do to stay sane when they're far from home. The windows, when there are windows, are small and thick, triple pane with layers of glass or polycarbonate to hold back the vacuum and filter the harsh, unmodulated sunlight. Looking through one, you see the familiar gray landscape, the black sky, the stars that don't twinkle in the airless void. And there, hanging above the horizon, is Earth, a brilliant blue and white marble, so vivid against the darkness that it almost hurts to look at. That view becomes precious, a reminder that home is only a few days away, 250,000 miles across space, but still visible, still there. The settlement grows in stages, each mission adding a few more modules, a few more capabilities. There's a workshop where tools and equipment can be maintained and repaired. There's a medical bay, small but equipped to handle the most likely emergencies. There's a laboratory for analyzing lunar samples and conducting experiments. There's storage for food, water, spare parts, all the things that can't be manufactured locally yet. And slowly, over years, the collection of buried modules and printed domes begins to feel less like a construction site and more like a village. People name the different sections. The galley, the ops center, the rec room. Paths get worn between structures, tracks in the dust where people walk most frequently. Equipment gets parked in familiar spots. It's not home, not in the way Earth is home, but it's a place that humans inhabit, a place that reflects human presence and human needs. At night, during the 14 days of darkness, the settlement becomes a constellation of tiny lights. The glow from windows and external lights creates small pools of illumination in the absolute dark. From orbit, it would look like a small town, a cluster of lights in the vast empty gray. And inside, behind those lights, people are living their lives, eating and sleeping and working, carrying on despite being in one of the most inhospitable environments humans have ever tried to inhabit. Building these first homes takes patience and care. Every element must work correctly, every seal must be perfect, every system must have backups. Lives depend on the integrity of these structures, on the layers of fabric and regolith that hold back the vacuum, on the machines that maintain breathable air and drinkable water. But humans are good at making homes in difficult places. We've done it in deserts and Arctic tundra, on mountains and in valleys prone to flooding. The moon is more extreme, more unforgiving, but the principle is the same. Find shelter, create safety, make a space that protects you from the environment outside. And once that space exists, once those first habitats are in place and people are living in them safely, everything else becomes possible. Water is life, even on the moon. Without it, a lunar settlement is impossible. With it, everything changes. Water can be split into oxygen to breathe and hydrogen for fuel. It can be used to grow plants, to cool equipment, to provide the basic needs of human biology. And remarkably, surprisingly, the moon has water, locked away in places where the sun has never shined. Near the poles, there are craters, deep and ancient, whose floors have been in shadow for billions of years. The moon's axis is nearly perpendicular to its orbit, tilted only about 1.5 degrees, which means the sun never rises high in the polar sky. It just schemes along the horizon, circling endlessly, creating areas that never see direct sunlight. The floors of these polar craters are the coldest places in the solar system, hovering at around 370 degrees below 0 Fahrenheit, cold enough to trap even the most volatile substances. Over geological time, these cold traps have been collecting water. Some of it comes from comets that struck the moon, vaporizing on impact, but with some of their water molecules migrating to these permanently shadowed regions and freezing there. Some comes from the solar wind, hydrogen ions that impact the lunar surface and combine with oxygen in the rocks to form water molecules, which then migrate until they reach the cold traps. And some might come from volcanic activity early in the moon's history, water outgassed from the interior and frozen in these natural freezers. The water isn't liquid, of course. It's ice, mixed in with the regolith, creating a layer of frosty soil. The concentrations vary. In some places, the regolith might be 5 or 10% water ice by weight. In the very coldest spots, there might be patches of nearly pure ice, layers that have accumulated over immense periods of time. Finding this ice was one of the early priorities for lunar exploration. Orbital missions with spectrometers and radar mapped the polar regions, looking for the signature of hydrogen, the telltale sign of water ice hiding in the shadows. Robots landed in these dark craters, drilling and sampling, confirming what the orbital data suggested. The ice is there, billions of tons of it, waiting. Extracting this ice is a slow, methodical process, peaceful in its repetition. Mining operations in the permanently shadowed craters are unlike any mining on Earth. First, there's the darkness. These places have never seen sunlight, and bringing light into them feels like an intrusion, a violation of ancient silence. Work lights on rovers and excavators create small bubbles of illumination, stark white or pale yellow against the absolute black, making the shadows even more dramatic. The equipment moves carefully. Rovers with drill rigs bore into the regolith, collecting samples, analyzing them for water content. When a good deposit is found, excavators begin to dig, scooping up the icy soil and loading it into containers. The material is cold, so cold that it can damage equipment if not handled properly. Everything has to be designed to operate at these extreme temperatures, with heaters to keep joints flexible and electronics functional. The icy regolith is transported to a processing facility, probably located just outside the permanently shadowed region where solar panels can provide power. Here, the extraction happens. The simplest method is heating. The regolith is placed in ovens or chambers and gently warmed. The ice sublimates, turning directly from solid to vapor without melting, and the vapor is collected and condensed back into water. This process requires patience. You can't heat the soil too quickly or too hot, or you'll waste energy and possibly damage your equipment. The extraction happens at a steady, measured pace, the temperature carefully controlled. Slowly, the water vapor collects on cold surfaces inside the extraction chamber, forming frost, which then melts into liquid water that drains into storage tanks. The leftover regolith, now depleted of ice, is moved aside, and a new batch is loaded in. Hour after hour, day after day, the process continues. It's not dramatic. It's industrial, repetitive, like any other mining operation, except that it's happening in darkness and cold that would freeze carbon dioxide solid, and the prize being extracted is something as mundane and precious as water. The water that comes out isn't pure at first. It contains dissolved gases, minerals, perhaps traces of organic compounds brought by comets billions of years ago. It's filtered and purified, passed through treatment systems until it meets the standards for human use. Some of it is stored as water, kept in insulated tanks. Some is immediately split into hydrogen and oxygen, either by electrolysis or other processes, providing breathable air and fuel for rockets. Imagine the satisfaction of watching those storage tanks fill, liter by liter. Each liter represents resources that didn't have to be launched from Earth, mass that was already on the moon, waiting to be used. The first time a settlement produces enough water from local sources to meet all its needs, it's a milestone, a moment when dependence on Earth decreases and self-sufficiency increases. The hydrogen and oxygen produced from lunar water have multiple uses. The oxygen is obviously critical for life support, but it's also useful for many industrial processes. The hydrogen can be combined with oxygen in fuel cells to produce electricity and water, creating a cycle. Or it can be stored as rocket fuel. A rocket leaving the moon needs much less fuel than one leaving Earth because the moon's gravity is only 1/6 as strong, but it still needs fuel, and hydrogen and oxygen make an excellent propellant. Over time, the mining operations expand. More craters are explored, more deposits are found and exploited. Automated systems do most of the work, robots that can operate in the extreme cold and darkness, scooping and hauling and processing without needing light or warmth or rest. Humans supervise from control centers, monitoring the systems, making adjustments, but the actual labor is mechanical, tireless, endlessly patient. There's something almost meditative about these operations. The rhythm of extraction, the steady accumulation of resources, the transformation of frozen ancient ice into the fundamentals of life. In those dark craters, water that fell from the sky billions of years ago, perhaps delivered by comets from the outer solar system, is being liberated and used to sustain human presence on another world. The permanently shadowed regions remain dark, mostly. The mining operations bring temporary light, moving pools of illumination that advance as the deposits are worked, then moving on, leaving the extracted areas to return to darkness. It feels respectful, somehow, not flooding these ancient places with permanent light but working in them gently, taking what's needed and then withdrawing. And high above, on the crater rims, the peaks of eternal light catch the sun and glow softly. Power stations are built there, fields of solar panels that generate electricity continuously, sending it down cables to the processing facilities below. The contrast is perfect. Light and dark, heat and cold, working together to provide the resources for life. The water becomes the foundation of everything. Without it, the settlement would be dependent on regular shipments from Earth, expensive and vulnerable to disruption. With it, the settlement can grow, supporting more people, enabling more activities. Greenhouses can be built, filled with plants that need water to grow. Industry can expand, using water for cooling and as a feedstock for chemical processes. Rockets can be fuel for trips back to Earth or onto other destinations. In time, enough water is extracted that some of it can be used for comfort rather than just necessity. There might even be enough for a shower, a real shower with water that cascades down in the low gravity, falling slowly, each droplet taking its time. After months of sponge baths and ration water, that would feel like the greatest luxury imaginable. The ice in those dark craters represents millions of years of accumulation, and even with extensive mining, the reserves are vast enough to last for generations. The moon is sharing its hidden treasures, resources that have been waiting in the cold and dark, preserved perfectly, ready to support the next chapter of human exploration. And so, the water flows, molecule by molecule, from the eternal shadows into the light, transformed from ice to vapor to liquid, split into its elements and recombined, used and reused in the closed cycles that make life possible on an airless world. There's something deeply satisfying about the idea of green growing on the moon. Plants reaching toward grow lights, roots spreading through lunar soil enriched with earth nutrients, oxygen being produced by photosynthesis in the one place in all the universe besides Earth where humans are trying to live. It's a connection to home, a piece of Earth transplanted and thriving in alien ground. The first greenhouse on the moon will be small, perhaps not much larger than a garden shed. It might be another inflatable module, specially designed with transparent panels to let in sunlight during the 14-day lunar day, or it might be entirely dependent on artificial lights during both day and night, maintaining a consistent growing environment regardless of the conditions outside. The structure itself is carefully designed. The walls need to be strong enough to contain the internal pressure, transparent enough to allow light through, and insulated enough to maintain a stable temperature. During the lunar day, the sun's unfiltered radiation pours down with an intensity that would quickly cook any unprotected plant. During the lunar night, the cold is so extreme that any heat radiates away almost instantly. So the greenhouse needs active temperature control, cooling systems for the day and heating systems for the night, maintaining the narrow range that plants need to thrive. Inside, the atmosphere is enriched with carbon dioxide, giving the plants more of the gas they need for photosynthesis. The air pressure is lower than Earth normal, perhaps just enough to keep water liquid and plants alive, reducing the stress on the structure's walls. The temperature is kept in a comfortable range for growth, warm but not hot, around 70 or 80 degrees. And then there's the soil, or rather, the growing medium. Lunar regolith by itself is terrible for plants. It's essentially powdered rock, with no organic matter, no nitrogen, no nutrients that plants need. It's also extremely alkaline, with a pH that would burn sensitive roots. And it contains sharp glassy particles and toxic compounds like perchlorates that would poison most plants. But regolith can be modified, transformed into something that plants can tolerate. The process starts with mixing the lunar soil with organic matter brought from Earth, compost or biochar or similar materials that add carbon and create structure. Then nutrients are added, nitrogen and phosphorus and potassium, the basic elements that all plants need. The pH is adjusted with additives, bringing it down from extremely alkaline to something closer to neutral. The perchlorates are washed out, dissolved in water and disposed of safely. What emerges is a hybrid growing medium, part lunar and part terrestrial, dark gray instead of the pure gray of regolith, crumbly and textured instead of smooth and dusty. It's not quite soil, not yet, but it's close enough to grow plants in, especially tough pioneering species that can tolerate less than ideal conditions. The first plants grown on the moon will probably be chosen for speed and utility. Things like lettuce and radishes, fast-growing crops that can provide fresh food in a matter of weeks. Herbs like basil and mint that add flavor to the bland preserved food that makes up most of the lunar diet. Maybe dwarf wheat or rice, staple grains that store well and provide calories. The planting is done carefully. Seeds are pressed into the growing medium, covered lightly, and watered. The water is precious, every drop accounted for, and the irrigation system is designed to waste nothing. Drip lines deliver moisture directly to the roots. Humidity in the greenhouse is captured and condensed, returning water to the system. Every exhaled breath, every drop of plant transpiration is recycled endlessly. And then, the waiting. In the controlled environment of the greenhouse, with the right temperature and humidity and light, the seeds begin to germinate. Tiny shoots push up through the gray-tinged soil, pale green at first, then darker as their chlorophyll develops. Day by day, they grow, leaves unfurling, stems reaching upward in the low gravity. Lunar gravity is only 1/6 of Earth's, and plants respond to this in interesting ways. They don't need as much structural support, so some species grow taller and lankier than they would on Earth. Others seem confused, their normal gravitropic response is altered by the weaker pole. Researchers have to learn how different crops behave in low gravity, adjusting their techniques, breeding varieties that are adapted to these conditions. The lighting is crucial. During the lunar day, natural sunlight can be directed into the greenhouse through windows or fiber optic cables, intense and free. During the long night, artificial lights take over, LEDs tuned to the specific wavelengths that plants use most efficiently for photosynthesis. The lights glow pink or purple, the combination of red and blue that chlorophyll absorbs best, giving the greenhouse an alien appearance even as it nurtures familiar Earth life. Watching the plants grow becomes a form of meditation. There's not much else that changes visibly on the moon. The landscape outside is static, eternal, the same craters and plains that have been there for eons. But inside the greenhouse, life is happening. Growth, change, the daily miracle of photosynthesis turning carbon dioxide and water into sugars and oxygen. The first harvest is a moment of celebration. Lettuce leaves are cut carefully, washed, and eaten fresh. After months of freeze-dried and vacuum-packed food, the taste of something crisp and green and alive is almost overwhelming. It's not just nutrition, though the vitamins are welcome. It's the psychological boost, the connection to Earth and to the rhythms of agriculture that humans have followed for thousands of years. As the agricultural program expands, more species are added. Tomatoes, though they need careful support and pollination in the absence of wind and insects. Strawberries, their runners spreading through the growing medium. Potatoes, grown in bins where the tubers can be harvested without disturbing the plants too much. Beans and peas, nitrogen fixers that actually improve the soil they're grown in, their root nodules hosting bacteria that convert atmospheric nitrogen into forms that plants can use. Some of the plants are grown not for food but for other purposes. Bamboo or hemp for their fast-growing fibers, which can be used to make textiles or paper or composite materials. Algae and photobioreactors, producing oxygen and edible biomass efficiently, their green slurry less appetizing than fresh vegetables but nutritionally complete. The greenhouse becomes a place of refuge, a space that's psychologically different from the rest of the settlement. It smells like soil and growing things, earthy and organic. It's full of green, a color almost absent everywhere else on the moon. The sounds are different too, the gentle hum of fans and water pumps instead of the mechanical noises of life support systems. People volunteer to work in the greenhouse, not because they have to, but because it makes them feel better, more grounded, more connected to life. Over time, the amount of food produced locally increases. Never enough to be completely self-sufficient, at least not at first, but enough to make a difference. Fresh supplements to the preserved rations, variety in the diet, the pleasure of eating something that was growing an hour ago instead of something that's been in storage for months. The waste from the settlement, the organic waste, gets composted and added back to the growing medium, slowly building up the organic content, making it richer and more like real soil. It's a closed loop, resources cycling from plants to humans and back to plants again, the way they do on Earth, but more consciously, more deliberately managed. There are setbacks, of course. Crops fail sometimes, diseases or pests brought accidentally from Earth spread through the tightly packed plants. Equipment breaks down, temperature swings damage sensitive seedlings, human error leads to wilted or flooded beds. But the overall trend is toward success, toward improvement, as techniques are refined and experience accumulates. In some visions of the future, there are large agricultural domes, acres under glass and regolith, fields of grain waving slowly in the recycled air, orchards of dwarf fruit trees carefully pruned and trained. The reality will probably be more modest, at least at first, but the principle is sound. Anywhere humans settle for the long term, they'll want to grow their own food, to have that connection to the soil and the satisfaction of nurturing life. And perhaps most importantly, the plants are doing what plants do best, taking carbon dioxide and producing oxygen. In a closed environment like a lunar settlement, that's not just useful, it's essential. The mechanical life support systems can produce oxygen by splitting water, but that requires energy. Plants do it for free, powered by light, and they do it beautifully, quietly, each leaf a tiny factory performing the miracle of photosynthesis. So the greenhouses grow, slowly, new modules added as resources allow, more species introduced, the agricultural knowledge base expanding. And inside these small pockets of carefully maintained earth environment, life flourishes, green and growing, a testament to the adaptability of biology and the determination of humans to bring life wherever they go. Of all the sights on the moon, the most powerful, the most emotionally resonant, is the view of Earth. Our home world, hanging in the black sky, brilliant blue and white, swirled with clouds, showing hints of continents and oceans. It's small enough to cover with your thumb held at arm's length, yet large enough to fill your heart with longing. From most of the lunar surface, Earth doesn't rise or set. The moon is tidally locked, always showing the same face to Earth, which means that from the near side, Earth hangs in roughly the same position in the sky always, barely moving, fixed in place like a celestial ornament. It rotates slowly, showing different faces as it spins, but it doesn't cross the sky the way the sun and moon do as seen from Earth. But from the polar regions, where most settlements are likely to be built, Earth sits low on the horizon, peeking over the crater rims, sometimes visible and sometimes hidden depending on exactly where you are. And from orbit, or from the far side, Earth does rise and set, emerging from behind the lunar horizon and disappearing again, though much more slowly than the quick sunrise and sunset we're used to. Imagine standing in an observation dome, looking out through the thick windows at the landscape and the sky beyond. The stars are everywhere, thousands upon thousands of them, more than you've ever seen from Earth even on the clearest, darkest night, because there's no atmosphere to scatter their light, no light pollution to drown them out. They don't twinkle. They shine steadily, points of pure light against the absolute black of space. And there, low in the sky or perhaps higher depending on your latitude, is Earth. It's so much more vivid than anything else in view. The moon is gray and black and white, but Earth is color, the deep blue of the oceans, the white swirls of cloud systems, the browns and greens of continents. If you're lucky with the timing, you might see the glint of sunlight reflecting off an ocean, a bright spot called the specular reflection, Earth sees acting like mirrors. During Earth's day, the illuminated side is brilliant. You can see weather systems, the spiral of hurricanes, the long bands of clouds along fronts. You can see the ice caps at the poles, white and gleaming. At the terminator, the line between day and night, you can sometimes see the lights of cities, tiny clusters of artificial light marking human civilization. As Earth rotates, you see different parts of the globe. The vast Pacific Ocean, so much water that it's hard to believe a planet could have that much liquid on its surface. The Americas, north and south, their shapes familiar from maps but rendered new and strange by the perspective of space. Africa and Europe and Asia, continents that have been home to humans for hundreds of thousands of years. Australia, isolated and ancient. Antarctica, white and empty at the bottom of the world. The clouds change constantly. Weather patterns develop and dissipate, storms form and fade, fronts march across latitudes. You can watch the same region over hours or days and see the weather transform, clouds gathering or clearing, the interplay of ocean and atmosphere that drives Earth's climate. At night, the dark side of Earth isn't completely dark. City lights trace out coastlines and mark population centers. The megalopolises glow bright, interconnected webs of light showing where millions of people live and work. Highways appear as lines of light connecting cities. And here and there, more isolated lights mark smaller towns, ships at sea, remote stations. There are times when the view becomes particularly special. During a solar eclipse, Earth's shadow falls on the moon, and from the moon you can watch Earth block out the sun, a black disk surrounded by a ring of light as the atmosphere refracts sunlight around the edges. During a lunar eclipse, which from the moon's perspective is Earth transiting the sun, the Earth becomes a dark circle rimmed with red, the combined light of all Earth's sunrises and sunsets bend around the edge of the planet. For the people living on the moon, Earth becomes a psychological anchor. It's a reminder that you're not truly isolated, that home is still there, close enough to see in detail, close enough that help could reach you in a few days if needed. It's a source of beauty in an environment that's mostly monochrome and harsh. And it's a symbol of everything you've left behind: family and friends, forests and oceans, blue sky and breathable air. Some settlements might orient their common areas and living quarters to have views of Earth. Windows would be positioned to frame that blue marble, making it a constant presence in daily life. People would glance up from their work and see home, a small comfort that makes the isolation more bearable. There would be times when Earth is particularly breathtaking. During the lunar day, with the sun shining from behind you, Earth is a full disk, fully illuminated, showing its complete face. During the lunar night, when the sun is behind Earth from your perspective, you might see Earth as a crescent, a thin arc of light with the dark side faintly visible, lit by reflected light from the moon itself, Earth's shine on Earth. Photographers on the moon would probably never tire of shooting Earth. The view changes constantly as the planet rotates, as clouds move, as seasons progress in the northern and southern hemispheres. Some might specialize in capturing specific features, the Himalayas standing out in relief, the Amazon basin lush and green, the Sahara vast and tan. And there would be moments of acute homesickness, times when seeing Earth so close yet so unreachable would be painful. Times when you'd want to be there, walking on grass, feeling wind on your face, smelling rain, all the things that are impossible on the moon. The psychological challenges of lunar settlement are real, and the sight of Earth, while comforting, can also be a reminder of everything you're missing. But for the most part, Earth's presence in the lunar sky is a blessing. It's a connection, a link, a reminder that the moon is not a separate world but a companion to Earth, bound together by gravity and by the spreading thread of human presence. Every person on the moon came from that blue sphere, and someday, most will return to it, carrying with them memories of what it looked like from the outside, small and beautiful and fragile. The fragility becomes apparent from the moon. Earth's atmosphere is a thin shell, barely visible as a pale blue band at the horizon. The biosphere, all the life that makes Earth unique, is confined to the thinnest layer on the surface. From 250,000 miles away, you can see how small and vulnerable our world is, how precious it is in the vast emptiness of space. This perspective, this overview effect as it's sometimes called, changes people. Astronauts who've seen Earth from space often report a shift in their understanding, a deeper appreciation for the planet and a sense of the interconnectedness of all life on it. For For people living on the moon, that sense would be constant, reinforced every time they look up and see their home world hanging in the sky. At night, in the recreation areas of the settlement, people might gather just to watch Earth. It becomes a shared experience, a communal contemplation. Someone points out a hurricane forming in the Atlantic. Someone else notices the lights of their hometown, a tiny bright spot among millions. The conversation is quiet, reflective, full of longing and wonder. And children born on the moon, if settlements last long enough for that to happen, would grow up with Earth as a presence in their sky. It would be the world of stories, the place their parents came from, the planet with blue skies and trees and animals and weather. For them, the moon would be home, and Earth would be the exotic destination, the place they might visit someday if they're willing to endure the strain of 6 times their accustomed gravity. But for the first generations, the ones who made the choice to live on the moon, Earth remains home in a way the moon can never fully replace. And its presence in the sky, constant and beautiful and just out of reach, is both a comfort and a reminder of the price of being pioneers. If you travel to the far side of the moon, the side that never faces Earth, you enter a realm of silence unlike anywhere else accessible to humans. Earth is blocked by the entire mass of the moon, roughly 2,000 miles of rock and metal, and with Earth goes all the radio noise of human civilization. No television signals, no radar, no cell phone chatter, no navigation satellites, nothing. It's the quietest place in the inner solar system, a refuge from the electromagnetic chaos that surrounds our home planet. The far side looks much like the near side, at first glance. Gray regolith, craters upon craters, ancient surfaces undisturbed for billions of years. But there are differences. The far side has fewer maria, less of the dark volcanic plains that mark the near side. Instead, it's dominated by highlands, lighter-colored terrain that's older and more heavily cratered. The crust is thicker on the far side, which may be why less lava made it to the surface in the moon's early history. One of the most dramatic features of the far side is the South Pole Aitken Basin, an immense impact crater near the southern pole. It's one of the largest impact structures in the solar system, about 1,500 miles across and more than 5 miles deep. The asteroid or comet that created it struck with unimaginable violence, excavating deep into the moon's crust, perhaps even reaching the mantle. The floor of the basin is darker than the surrounding highlands, and the impact threw up mountain ranges at its rim that are visible from orbit as concentric rings of elevated terrain. But what makes the far side truly special isn't its geology, it's its radio silence. On Earth, we're bathed constantly in radio waves. Every radio and television station, every cell tower, every Wi-Fi router, every radar installation is broadcasting, filling the spectrum with signals. Even in remote areas, satellites overhead add their transmissions to the mix. For radio astronomers trying to observe faint signals from distant galaxies or the early universe, this interference is a constant challenge. On the moon's far side, all of that goes away. The moon itself acts as a shield, blocking Earth's radio emissions completely. During the lunar night, when the sun is also blocked, it's possible to achieve a level of radio quietness that's impossible anywhere else in the near-Earth environment. This makes the far side ideal for radio astronomy, particularly for observing at frequencies that are completely blocked by Earth's ionosphere or swamped by human interference. Imagine a radio telescope constructed in a far side crater. It might be a simple design, just wires laid out on the regolith in patterns designed to receive specific frequencies. Or it could be more elaborate, a dish built by robots from lunar materials, shaped precisely to focus radio waves to a detector. The telescope operates autonomously, collecting data during the long lunar night, storing it for transmission back to Earth when communication satellites come into view over the horizon. This telescope could observe the cosmic dark ages, the period after the Big Bang when the universe had cooled enough for hydrogen atoms to form but before the first stars ignited. The signature of this era is a very specific wavelength of radio emission from neutral hydrogen, redshifted by the expansion of the universe into frequencies that are best observed from the moon's far side. Understanding this period would tell us about the early universe, about how matter was distributed, about the conditions that led to the formation of the first stars and galaxies. Or the telescope might search for radio signals from exoplanets, listening for the kind of auroral emissions that planets with magnetic fields produce. Jupiter is bright in radio wavelengths because of this effect, and other gas giants and other solar systems might be as well. Detecting these signals would tell us about those planets' magnetic fields, their rotation rates, maybe even about interactions with their parent stars. The far side is also scientifically interesting for other reasons. Because it's never seen Earth, it hasn't been contaminated by debris from terrestrial spacecraft. The regolith there contains a pure record of the solar system's history, uncontaminated by anything from Earth. Samples collected from the far side could be analyzed to understand the flux of cosmic rays and solar particles over billions of years, providing insights into the sun's behavior and the interstellar environment the solar system has traveled through. But the far side is also profoundly isolating. When you're there, you can't communicate with Earth directly. Radio waves don't bend around the moon, and there's no atmosphere to bounce signals off. To talk to Earth, you need relay satellites, spacecraft positioned at Lagrange points or in lunar orbit that can see both Earth and your location on the far side. There's a delay even with perfect relay infrastructure, and if the relay fails, you're cut off completely. Settlements on the far side, if they're ever built, would be among the most isolated human outposts imaginable. Help from Earth is days away. Help from near-side settlements requires crossing hundreds or thousands of miles of rugged lunar terrain. You're dependent entirely on your local resources and your own capabilities. But that isolation might appeal to some. The far side would attract scientists who want the radio quiet for their research, but also perhaps people who want distance from human civilization, even the limited human civilization on the near side. It would be a place for those who seek solitude, who find peace and emptiness and silence. Imagine a small research station in a far side crater, a cluster of habitats and laboratories built into the crater wall. Outside, robotic excavators and sintering machines are constructing a radio telescope, laying out elements in a precise pattern across the crater floor. Inside, a small team of astronomers and engineers monitor the construction, analyze data from preliminary observations, and maintain the systems that keep them alive. The work has a rhythm. During the lunar day, which here on the far side is still 14 Earth days long, the radio telescope is powered down. The sun's radio emissions swamp any faint cosmic signals, and the heat is challenging for electronics anyway. This is the time for maintenance, for construction, for sleeping through the worst of the heat. The habitats are well insulated and temperature controlled, but there's still a sense of waiting for the day to end. When the lunar night finally arrives, the temperature plummets and the telescope comes alive. The sky is black, perfectly black, without even Earth's reflected light to brighten it. The stars are brilliant, and the Milky Way is a river of light across the sky, so dense with stars that it's hard to pick out individual points. The radio telescope begins its observations, sweeping through frequencies, collecting photons that have traveled across the universe for billions of years. The data accumulates slowly. Radio astronomy is often about patience, about long integration times, about collecting enough signal to rise above the noise. The astronomers watch in near real time, but the really interesting analysis will happen later, after months or years of data have been gathered and processed. Still, there's excitement in the observation itself, in knowing that you're listening to the universe from the quietest place humans have ever been. Communication with Earth happens through scheduled transmission windows, times when the relay satellites are in position. The team composes messages, sends data files, receives updates and news from home. And then the link closes, and they're alone again, isolated behind 2,000 miles of rock, working in the silence. The psychological impact of this isolation is hard to predict. Some people might find it liberating, a relief from the constant connectivity of modern life. Others might find it oppressive, the lack of real-time communication with Earth stressful and alienating. Selection and training for far-side missions would need to account for this, choosing people who can handle extended periods of isolation and delayed communication. But there's also a strange beauty to it. In the silence, you can hear yourself think. In the isolation, you can focus. The work becomes meditative, the observation's a form of contemplation. You're not just studying the universe, you're experiencing a part of it that few other humans ever will, a place where the noise of civilization falls away and leaves only the cosmos and your own thoughts. Over time, the far side might develop its own culture, distinct from the near side settlements. People who spent years in the radio quiet might find it hard to return to places where communication is constant and immediate. They might prefer the slower pace, the deliberate nature of scheduled communications, the long periods of uninterrupted work. And the discoveries made there could reshape our understanding of the universe. The radio observations from the far side could reveal details about the cosmic dawn, about the formation of the first stars, about the distribution of matter in the early universe. They could detect signals from exoplanets, opening a new way to study worlds around other stars. They could even, possibly, detect signals from extraterrestrial intelligence, though that remains speculative. The far side is a resource, a unique environment that can't be replicated anywhere else near Earth. As lunar settlement expands, it will inevitably draw people there, scientists and technicians and support staff, all working together in one of the most isolated and silent places humans have ever inhabited. And in that silence, they'll listen to the universe, gathering whispers from the distant past and the far reaches of space, adding to our collective understanding of everything that is. The journey between Earth and Moon is the most important transportation route in near-Earth space, the highway that carries people and cargo and ideas between our two worlds. It's a journey of roughly 240,000 miles, a distance that sounds enormous but in cosmic terms is almost nothing, a tiny gap between companions. The earliest lunar missions took about 3 days to make the trip, coasting most of the way after an initial boost from powerful rockets. Modern spacecraft might take slightly longer or slightly shorter depending on their trajectory and propulsion system, but 3 days remains typical. It's long enough to be a real journey, a period of transition between worlds, but short enough to be manageable with current life support technology. Imagine a cargo freighter designed for the Earth-Moon run. It's not sleek or elegant. It's a cluster of cylinders and spheres, fuel tanks and cargo modules, and a small pressurized section for the crew if there is a crew. Many are fully automated. Solar panels extend like wings, tracking the sun to generate power. The exterior is plain, white or silver to reflect heat, covered with sensors and communication antennas. The freighter sits in low Earth orbit, being loaded. Cargo containers are maneuvered into place by robotic arms, locked down, connected to power and data lines if they need them. Some containers hold consumables for the lunar settlement, food and water and air and spare parts. Others hold equipment, new modules to expand habitats, scientific instruments, personal items for the residents. Everything is carefully packed and secured because the journey involves periods of acceleration and microgravity where loose items would float free. When the loading is complete and the launch window arrives, the calculated time when the moon is in the right position for an efficient trajectory, the freighter's engines ignite. They're probably not chemical rockets, which are powerful but inefficient. More likely, they're ion engines or some other form of electric propulsion, using electricity from the solar panels to accelerate propellant to high speeds. The thrust is gentle, barely perceptible, but it's constant, applied over hours or days, gradually building up speed. The freighter spirals out from Earth, climbing through the radiation belts, passing the orbit of geostationary satellites. The curve of the Earth becomes more pronounced, the blue of oceans and white of clouds spreading out below. And then Earth begins to shrink, slowly at first, then more noticeably, dwindling from a vast curved surface to a disk to a sphere hanging in space. Inside the pressurized section, if there's a crew, the journey is quiet. Microgravity takes some getting used to if you're not accustomed to it. You float through the cabin, pushing off walls, grabbing handholds. Objects drift if not secured. Water forms perfect spheres that wobble through the air. Eating and sleeping and using the bathroom all require adaptation and technique. The view changes constantly. Earth recedes, its features becoming harder to distinguish. The moon grows larger, its craters resolving into detail, the Maria becoming distinct patches of dark against the lighter highlands. The sun is a point of intense light, blinding if you look at it directly, providing the energy that powers the ship. The stars are everywhere, unchanging, patient. Midway through the journey, there's a moment when Earth and Moon are roughly the same size in the windows, balanced, two worlds of similar apparent scale. It doesn't last long. The Moon continues to grow as Earth continues to shrink, the balance tipping as the ship is captured more by lunar gravity than terrestrial. As the freighter approaches the Moon, it needs to slow down. Coming in too fast would send it whipping around the Moon and back toward Earth, or worse, crashing into the surface. The engines fire again, a braking burn that lasts for minutes or hours depending on the ship's mass and propulsion system. The burn might happen in multiple stages, first to capture into a high elliptical orbit around the Moon, then to circularize that orbit, then finally to descend toward the landing site. The descent to the lunar surface is careful and precise. The freighter, or a smaller lander that detaches from it, fires its engines to drop out of orbit, falling toward the surface in a controlled trajectory. Sensors track the terrain below, matching it against maps, ensuring the landing site is clear of obstacles. As the surface approaches, the engine throttles up, fighting gravity, slowing the descent to a gentle touchdown. The landing legs make contact, compressing slightly, absorbing the shock. Dust kicked up by the engine plume settles immediately in the vacuum, falling back to the surface in perfect parabolas. The engine shut down, and there's silence. The freighter has delivered its cargo across 240,000 miles of space, and now it rests on the Moon, mission accomplished. Unloading begins quickly. Robots emerge from nearby facilities, or human crews in spacesuits, and start detaching containers, moving them to storage or directly to where they're needed. The freighter might rest for a while, or it might be quickly reloaded with return cargo, samples to be analyzed on Earth, manufactured goods from lunar industry, propellant produced from lunar water to refuel other spacecraft. For crewed spacecraft, passenger ships carrying people rather than just cargo, the journey is similar but with more attention to comfort. The habitat module is larger, with better life support, perhaps even some artificial gravity generated by spinning the ship or parts of the ship. There are windows for viewing, exercise equipment to prevent muscle and bone loss, communication systems to stay in touch with Earth and Moon. Passengers on these ships are often a mix of scientists rotating to and from lunar assignments, engineers and technicians, perhaps eventually tourists willing to pay for the experience of lunar travel. The journey becomes routine for frequent travelers, just another commute, the one with a view that never gets old. During the trip, there's time to adapt mentally. Leaving Earth, you watch your home world recede, and the psychological distance grows with the physical distance. You're committed now, on your way to another world, and there's no turning back until the mission is complete. Approaching the Moon, anticipation builds. The gray sphere grows larger, its features becoming familiar, and you prepare for arrival, for the strange low gravity, for living in habitats carved into regolith, for seeing Earth as a distant blue marble. The return journey is a mirror of the outbound trip. Launch from the Moon is easier than launching from Earth because the gravity is so much weaker and there's no atmosphere to fight through. The spacecraft lifts off, rising smoothly, accelerating away from the surface. The Moon shrinks below, its gray plains and craters flattening into a disk. And ahead, Earth grows, that blue beacon, swirled with white, home. Re-entry to Earth is the most dramatic part of the return. The spacecraft has to shed the velocity it gained falling down Earth's gravity well, and the most efficient way to do that is to use the atmosphere. Re-entry vehicles hit the upper atmosphere at miles per second, and friction with the air heats them to thousands of degrees. A glowing sheath of plasma surrounds the vehicle, and for a few minutes, communication is blocked by the ionization. Then the spacecraft slows, the heating decreases, parachutes deploy or wings extend, and the final descent to landing is controlled and gentle. Touchdown on a runway or splashdown in the ocean, and the journey is complete. The passengers emerge into gravity that feels heavy after weeks or months in Lunar 16G, into air that smells of salt or earth or jet fuel, into a world that's full of color and life and weather. Over time, this route becomes well traveled. Multiple spacecraft make the journey every month, carrying cargo and people, building the infrastructure that makes lunar settlement viable. There are traffic control protocols, orbital tracks that separate ships to prevent collisions, designated landing sites with the facilities to receive and dispatch spacecraft efficiently. The economics of this transportation are crucial. Launching from Earth is expensive, costing thousands of dollars per kilogram of payload. Anything that can be produced on the Moon reduces the need to launch it from Earth, saving costs. Water, oxygen, fuel, eventually construction materials and manufactured goods, all produced locally, making the settlement more self-sufficient and the transportation more affordable. And as technology improves, the journey might become faster or more comfortable. Advanced propulsion systems could cut travel time from 3 days to 1 day or less. Larger ships could carry more passengers and cargo, reducing per-person costs. Orbital infrastructure, fuel depots and repair stations and transfer hubs could make the journey safer and more efficient. The connection between Earth and Moon, this highway through space, is the lifeline that makes lunar civilization possible. It carries not just physical goods but also information and ideas, messages and media, the cultural exchange between two worlds. People on the Moon watch shows and read news from Earth. People on Earth follow the lives and work of lunar residents, fascinated by the ongoing adventure. And someday, perhaps, this route will be just one segment of a larger network. Ships traveling from the Moon to Mars, or to the asteroid belt, using the Moon as a staging point, refueling with lunar propellant, launching from lunar gravity rather than fighting Earth's deeper well. The Moon becomes not a destination but a waypoint, a port on the routes that spread human presence through the solar system. But for now, the Earth-Moon route is enough, a testament to human capability and ambition, a 3-day journey across vacuum that connects our cradle world to our first tentative step beyond it. There will come a time, if lunar settlement continues and grows, when children are born on the Moon. Not by accident or emergency, but by choice, as residents decide to start families and raise the next generation in the place they've come to call home. These children will be lunar natives, the first humans for whom the Moon is not a destination but a birthplace. Pregnancy and birth in lunar gravity are largely unexplored territory. We know that mammals have developed successfully in microgravity aboard space stations, but lunar gravity, though only 1/6 of Earth's, is still gravity, which might make crucial differences. There will be concerns about fetal development, about whether the musculoskeletal system develops properly without the full stress of Earth gravity, about whether the vestibular system that controls balance can calibrate correctly. The first lunar births will probably be preceded by extensive research with animals, careful monitoring of pregnant residents, protocols and facilities designed to handle any complications. Medical staff on the Moon will need training in obstetrics adapted to lunar conditions. The delivery rooms will have equipment to manage both normal births and emergencies, with the understanding that some complications might require evacuation to Earth, a journey of 3 days during which anything could happen. But assuming the births go well, the infants who arrive will be human, completely human, but adapted from the start to an environment that's alien to the rest of our species. They'll be lighter, because everything is lighter on the Moon. A baby that would weigh 8 pounds on Earth weighs less than 2 pounds on the Moon, making them easier for parents to hold and carry, reducing the strain on developing muscles and bones. As these children grow, they'll be stronger relative to their weight than Earth children. With less gravity to resist, the same muscle power produces greater effects. A lunar child could jump 6 times higher than an Earth child of the same strength, leap across rooms, climb with effortless grace. Play would take on new dimensions, games adapted to the low gravity, movements that would be impossible on Earth. But there are concerns. Without the constant stress of Earth gravity, bones might not develop the density they normally would. Muscles might not grow as strong. Cardiovascular systems might adapt to the easier work of pumping blood in low gravity, becoming less robust. These children might be perfectly healthy on the Moon but unable to visit Earth without extensive conditioning, or perhaps unable to tolerate Earth gravity at all without assistance. Countermeasures would be important. Exercise routines designed for growing bodies, equipment that simulates resistance, activities that promote bone and muscle development. perhaps suits that add weight, making the wearer heavier, providing more resistance to movement. The goal would be to keep options open, to allow these children to visit Earth if they choose to, while still letting them enjoy the benefits of lunar gravity. Their worldview would be fundamentally different from their parents. For the first-generation settlers, Earth is home, the place they came from, full of memories and meaning. For children born on the moon, Earth is just another place, a world in the sky, full of strange things like weather and oceans and animals, but not inherently more special than the moon. Home is the habitat where they live, the corridors they run through, the greenhouses where they help tend plants, the lunar surface they play on during carefully supervised excursions. They would grow up with Earth hanging in the sky, a constant presence, but distant. They'd learn about it in school, watch videos of forests and beaches, hear stories from adults who remember living there. But it would be abstract, theoretical, not something they've experienced directly. The first time a lunar-born child visits Earth, if they ever do, would be overwhelming. The sensations would be so different: the weight, the air moving across skin, the smell of rain, the sight of an unfiltered blue sky. Language might develop differently. Lunar children might have their own slang, words and phrases that make sense in the context of lunar life but sound strange to Earth ears. They might measure distances or sizes differently, using local references instead of Earth standards. Their sense of humor might be shaped by the unique experiences of growing up on another world, jokes about low-gravity mishaps or the strangeness of Earth that their parents wouldn't find as funny. Education on the moon would need to balance preparing children for the world they live in with teaching them about Earth and human history and culture. They'd learn physics and chemistry and biology, but with examples drawn from lunar experience. They'd study history, but with emphasis on space exploration and the settlement of the moon. They'd learn about Earth's biosphere, but as something exotic and distant, not as their immediate environment. Socialization would be challenging in a small population. The first lunar-born children might be few, growing up knowing everyone in the settlement, lacking the anonymity and diversity of larger communities. They'd form tight bonds, perhaps, but also might feel constrained by the smallness of their world. As the settlement grows and more children are born, this would ease, but the early generations would face unique social challenges. There might be tensions between Earth-born and Moon-born residents. Different perspectives, different priorities, different senses of identity and belonging. The Earth-born might see themselves as pioneers and the Moon-born as privileged to grow up in a place their parents fought to establish. The Moon-born might see the Earth-born as outsiders, temporary residents who could leave any time, while they're committed to the Moon for life. But there would also be cooperation and mutual respect. The Earth-born parents would work hard to give their lunar children the best life possible, adapting Earth traditions to lunar circumstances, creating new traditions that fit the new world. The lunar children would grow up valuing the sacrifices their parents made, understanding that the settlement they inhabit was built with enormous effort and dedication. Celebrations and holidays would take on lunar character. Birthdays might be counted in Earth years for consistency, but there might also be recognition of lunar days, the long cycles of light and dark. Holidays from Earth would be celebrated, but adapted, Christmas or Diwali or Ramadan observed in habitats under regolith, traditions maintained but transformed by the new context. And as these children grow into adolescents and then adults, they'll face choices about their future. Do they stay on the moon, contributing to the community that raised them, or do they leave for Earth or other settlements? If they stay, what roles will they fill? Scientists and engineers and technicians, certainly, but also artists and teachers and leaders, people who shape lunar culture and society. Some might feel a calling to return to Earth, to see the place their parents came from, to experience the world that looms so large in stories and education. The journey would be challenging, arriving in 6 times the gravity they're used to, struggling with the weight, undergoing rehabilitation to build the strength and endurance to function normally. But for some, it would be worth it, the desire to understand their roots and heritage outweighing the difficulty. Others might feel more adventurous, looking beyond both Earth and Moon to other destinations. Mars, perhaps, with its own low gravity and frontier atmosphere. The asteroid belt, where gravity is negligible and resources are abundant. Lunar-born humans might be better adapted to low-gravity environments than Earth-born humans, making them ideal for exploring and settling other worlds. In time, if the pattern continues, there will be multiple generations born on the moon, families whose roots on the lunar surface go back decades or even centuries. These people will have no direct memory or experience of Earth, only what they've learned from records and stories. They'll be culturally distinct, a new branch of humanity adapted to life on another world. Their physiology might diverge, at least slightly, from Earth norms. Taller and lankier, perhaps, having grown in low gravity. Paler, if they spend most of their time indoors, or with different pigmentation adapted to the unfiltered solar radiation they encounter during surface activities. These changes would be subtle at first, but over many generations, they might become more pronounced, the beginning of a truly lunar human subspecies. But they'll still be human, with all that entails. The same emotions, the same needs for connection and meaning and purpose. The same curiosity and creativity and capacity for love. They'll look up at Earth and feel something, even if it's not the same thing their ancestors felt. They'll look out at the stars and wonder what's there, continuing the human tradition of exploration and questioning. The generation born on the moon represent a fundamental shift in human history. For all of our existence, humans have been Earth creatures, evolved on that one world, adapted to its particular conditions. But these children break that pattern, proving that humanity can take root elsewhere, that we're not forever confined to the place we started. And in the darkness of a lunar night, in a habitat buried under regolith, a parent might read a bedtime story to a child, tales of Earth with its vast oceans and endless sky, or stories of the moon about the first settlers and the slow patient work of building a new home. And the child, drifting off to sleep, dreams of both worlds, belonging to them both, shaped by them both, a true child of two planets. The moon waits for us still, patient as it has always been. The settlements we've imagined tonight are small steps, tentative reaches into a future that's not yet written. But they're possible, all of it, within the reach of current technology and human determination. As you drift towards sleep now, let these images settle gently in your mind. The gray landscape, ancient and peaceful. The first small habitats, humans making shelter in the dust. The ice hidden in eternal shadows, becoming water and oxygen and life. The plants growing in enriched regolith, green against gray. Earth hanging in the sky, beautiful and distant. The far side silence, radio quiet, listening to the universe. The ships that carry us back and forth, connecting two worlds. The children who will someday call the moon home, adapting to a lighter world, becoming something new while remaining fundamentally human. All of this is ahead of us, waiting in the future, as the moon has waited in the sky for billions of years. And tonight, as you sleep, the moon continues its orbit, pulling our tides, reflecting sunlight, constant and familiar, a companion to Earth and a destination for dreams. Rest now. Let your breathing slow. Let the images fade softly. The moon will still be there tomorrow, and every tomorrow after, waiting with infinite patience for the day we come to stay.